Regression analysis is perhaps the most commonly used statistical methodology out there. Regression analysis is used to quantify the relationships between one or more response variables and one or more explanatory or predictor variables. These models can be used to understand how and to what extent an outcome of interest varies in response to changes in one or more other variables. It's almost too obvious to point out that in standard regression analysis, the response variables and the explanatory variables are all observable. The input to a regression analysis is a dataset consisting of response variables and explanatory variables that have been measured on a number of subjects or experimental units. The observed data are then used to fit the regression model. This is so commonly understood and done, and we are so used to this process, that we may be led to think that in order to quantify regression-type relationships, the various quantities involved in those relationships must be directly observable and measurable. Interestingly, that is not the case. It is indeed possible to model one-way, explanatory, predictive, regression-type relationships among characteristics that are not directly measurable. Think about what I'm saying here. It's possible to understand how and to quantify to what extent an unobservable characteristic varies in response to changes in other unobservable characteristics. If one is not familiar with structural equation modeling, and perhaps even if you are, this is kind of mind-blowing stuff. To be able to quantify regression-type relationships among characteristics that you cannot even observe. The kind of unmeasurable characteristics that I'm talking about here are latent constructs, which are a common feature in structural equation models. In fact, some would say that latent constructs are one of the defining characteristics of structural equation models. We have seen several examples of structural equation models in previous lecture videos, and we have actually seen an example of modeling relationships among unobservable latent characteristics. In particular, we've looked at fitting and testing hypotheses about confirmatory factor analysis, or CFA, models. One of the primary features of confirmatory factor analysis models is that they model and quantify correlative two-way relationships among latent constructs. And so, perhaps it's not too big of a stretch to imagine that we could also model and quantify one-way predictive relationships among latent constructs. Models that are used to quantify predictive relationships among latent constructs are often called structural regression models. A structural regression model is a type of structural equation model, and so structural regression models can be fit using SEM software. And that is what we're going to do in this video. We're going to see how to use the CALIS procedure in SAS to fit a structural regression model, and we'll do this in the context of an example. So here's what we'll be looking at in this video. We'll first describe the structural regression modeling example. We'll then review the steps involved in specifying a structural equation model and provide a specification of the structural regression model. Once we've done that, we'll fit the structural regression model using the LinEQS programming language in SAS PROC CALIS. So let's jump in. So let's first provide a description of the example. Consider a structural regression model to determine the relationships among fluid intelligence components, namely a component called induction ability and one called figural relations ability. Induction ability during the junior year in high school and figural relations ability in each of the junior and senior years are considered to be latent constructs or factors. According to a proposed theory, 3 manifest variables are indicators of induction ability, 3 manifest variables are indicators of figural relations ability for the junior year, and 3 manifest variables are indicators of figural relations ability for the senior year. And so we see here that the latent construct figural relations ability is a latent construct that is assumed to be able to change over time. And so we are going to have latent constructs for both the junior and senior years for this figural relations ability construct. The 9 manifest variables were measured on 220 high school students. Each variable was measured on each student, so there was no missing data for any of the variables. Each variable in the dataset was centered at 0, but the variables were not scaled. Therefore, each variable exhibits its originally observed variation. Summary statistics consisting of the sample variances of the variables and the covariances between each pair of variables were calculated, and hence the sample covariance matrix is available for use in fitting the model. The sample covariance matrix is shown on the next slide. And so here we have the 9x9 sample covariance matrix for the 9 manifest variables. Next, let's review the steps involved in specifying a structural equation model. Step 1 is to identify all latent constructs or factors, as well as the manifest variables comprising the SEM. Step 2 is to specify an equation for each one-way, explanatory, predictive relationship in the SEM. Step 3 is to specify notation and/or values for the variances of all random variables in the system, as well as for all covariances of pairs of random variables. Step 4, identify and count the number of model parameters that need to be estimated. Step 5 is to construct a path diagram for the SEM. And then finally, step 6, we're going to fit the SEM in SAS. So let's look at step 1. Identify all latent constructs and manifest variables comprising the SEM. And so we have 3 latent constructs or factors. F1 represents the induction ability during the junior year. F2 represents the figural relations ability during the junior year. And F3 represents the figural relations ability during the senior year. Here are the manifest variables. V1, V2, and V3 are the junior year induction scores 1, 2, and 3 respectively. V4, V5, and V6 are the junior year figural relation scores 1, 2, and 3 respectively. And finally, V7, V8, and V9 are the senior year figural relation scores 1, 2, and 3 respectively. Here is a table that shows a little more information about how these variables are related. So in the left-hand column, we've got the name of the types of manifest variables. So we have induction scores and figural relation scores. And for each, we have 3 variables, 3 indicators. So we have induction score 1, induction score 2, and induction score 3. We have figural relation score 1, figural relation score 2, and figural relation score 3. Now, induction scores 1, 2, and 3 are each measured one time in the junior year only, and the corresponding variables are V1, V2, and V3. On the other hand, figural relation scores 1, 2, and 3 are each measured twice, once in the junior year and once in the senior year. And so V4 and V7 represent repeated measures on the figural relation score 1 variable, V5 and V8 represent repeated measures for the figural relation score 2, and V6 and V9 represent repeated measures for figural relation score 3. Next, let's look at the indicators for each latent construct. And so the indicators for F1, the induction ability during the junior year, are V1, V2, and V3. The induction scores 1, 2, and 3 during the junior year. The indicators for F2, the figural relations ability during the junior year, are V4, V5, and V6. And the indicators for F3, the figural relations ability during the senior year, are V7, V8, and V9. Next, let's look at step 2. Specify an equation for each one-way, explanatory, predictive relationship in the structural equation model. And so the equations for the dependence of the manifest variables V1, V2, and V3 on the latent construct induction ability during the junior year, or F1, are as follows. V1 is equal to lambda 1 times F1 plus E1. V2 is equal to lambda 2 times F1 plus E2. V3 is equal to lambda 3 times F1 plus E3, where E1, E2, and E3 are error terms. Equations for the dependence of the manifest variables V4, V5, and V6 on the latent construct F2, the figural relations ability during the junior year, are as follows. V4 is equal to lambda 4 times F2 plus E4. V5 is equal to lambda 5 times F2 plus E5. And V6 is equal to lambda 6 times F2 plus E6. Equations for the dependence of the manifest variables V7, V8, and V9 on the latent construct F3, the figural relations ability during the senior year, are as follows. V7 is equal to lambda 7 times F3 plus E7. V8 is equal to lambda 8 times F3 plus E8. V9 is equal to lambda 9 times F3 plus E9. And finally, here are the equations for the dependence of the latent constructs F2 and F3 on other latent constructs. So F2 is equal to beta 21 times F1 plus an error term D2. F3 is equal to beta 31 times F1 plus beta 32 times F2 plus the error term D3. Now look at this system and think carefully about what it represents. This structural equation model simultaneously models two unobservable response variables as linear functions of explanatory variables that are themselves unobservable. Now take a moment to wrap your head around that. Next, let's look at step 3. Specify notation and/or values for the variances of all random variables in the system, as well as for all covariances of pairs of random variables in the system. Now let's recall how to help ensure SEM identifiability. Raykov in 2000 gave 6 rules for determining which components in a structural equation model are model parameters in order to help ensure model identifiability. These rules are given on the following slides. And so rule number 1 says that all variances of independent variables are model parameters. Rule 2 says that all covariances between independent variables are model parameters as well. Now, rules 1 and 2 are talking about independent variables, and so these include exogenous explanatory variables as well as exogenous error terms. Rule 3 says, all factor loadings connecting the latent variables with their indicators are model parameters. Rule 4 says that all regression coefficients between observed variables or latent constructs are model parameters. Rule 5 says that all variances of dependent variables, the covariances between dependent variables, and the covariances between dependent variables and independent variables are never model parameters. And finally, Rule 6 says that for each latent construct included in a model, the metric of its scale, that is its variability, needs to be set. We use these rules to help identify which quantities in the model are parameters, those that need to be estimated, those that will not be estimated for identifiability purposes, and those that will be set to particular values, for example 0, for model simplicity. So with these things in mind, let's look at the assumed covariance relationships between error terms, between factors, and between factors and error terms that are going to be imposed on the model. By Rule 1, all variances of independent variables are model parameters, and this includes variances of error terms, and so the variances of the indicator error terms, the E sub i's, are model parameters, as are the variances of the error terms associated with the latent constructs F2 and F3. So we're going to estimate those, and so we'll need to define notation that we'll use for that purpose, and so this is the notation that we'll use in the software program. By Rule 2, all covariances between independent variables are model parameters, and so this includes covariances between error terms. We're going to be setting the covariances between pairs of the error terms equal to 0. And so you see that here, the covariance between E sub I and E sub j is going to be 0, where I is not equal to j. And we have 36 non-redundant covariances that are constrained to be 0 in this case. Also by Rule 2, the covariance of F1 and E sub j, j going from 1 to 9, are model parameters. And we're going to be setting those covariances equal to 0 as well. And so we have 9 covariances constrained to be 0 based on this line. By Rule 5, which says that the variances of dependent variables, the covariances between dependent variables, and the covariances between dependent variables and independent variables are never model parameters. So because of this, and because F2 and F3 are both dependent variables in this model, the covariance between F2 and F3 and each of the E sub j's, j going from 1 to 9, are all 0. And so we have 18 covariances that are constrained to be 0 by this requirement. By Rule 2, which says that all covariances between independent variables are model parameters, the covariance of F1 and each of D2 and D3 are model parameters, but we're going to be setting those equal to 0 in this model. And so there are 2 covariances constrained to be 0 by this line. And finally, by Rule 5, which again says that the variances of dependent variables, the covariances between dependent variables, and the covariances between dependent variables and independent variables are never model parameters. And so because F2 and F3 are both dependent variables in the model, the covariance of each one of these with each of the 2 error terms D2 and D3 are all equal to 0. And so there are 4 covariances that are constrained to be 0 based on this line. And so note that there are 69 non-redundant covariances constrained to be 0. Now regarding the variance of factor 1, by Rule 1, it is a model parameter, and so it either needs to be estimated or to be set to a particular value. In this model, we're going to estimate its value. By Rule 6, the metric of its scale needs to be set, and this is going to be done by setting the loading of its first indicator equal to 1. Regarding the variances of factor 2 and factor 3, by Rule 5, since F2 and F3 are endogenous or response variables, their variances are not model parameters to be estimated. Rather, the variability in each is modeled through their respective regression equations. By Rule 6, the metrics of the scale of each needs to be set, and this will be accomplished by setting the loading of the first indicator of each of these two latent constructs equal to 1. Next we have step 4. Identify and count the number of model parameters that need to be estimated. And so first we have the loadings. And so recall that lambda 1, lambda 4, and lambda 7 will each be set to 1 for identifiability and scaling purposes. And so we have 6 parameters to be estimated here: lambda 2, lambda 3, lambda 5 and lambda 6, and lambda 8 and lambda 9. We have one parameter, one variance of the factors to be estimated, and that is the variance of factor 1. We have 9 parameters to be estimated in terms of the variances of the indicator error terms, and 2 parameters to be estimated, which are the variances of the error terms associated with the regression equations for the latent constructs. And finally, we have 3 latent regression slopes that need to be estimated: beta 2.1, beta 3.1, and beta 3.2. And so we can see here that there are 21 parameters that need to be estimated in order to fit the structural equation model. Let's also calculate the model degrees of freedom. This can be compared with the output once we fit the model as one check that we have specified the model correctly to the SEM software. And so we have 9 manifest variables, V1 through V9. We've just shown that the number of parameters to be estimated is 21. And so the number of degrees of freedom associated with the model, which is the difference between the number of non-redundant entries in the covariance matrix and the number of parameters to be estimated, is 45 minus 21, or 24. Next, we have step 5, where we construct a path diagram for the model. On the path diagram, we're going to specifically identify the latent constructs, the manifest variables, the error terms, the endogenous variables, and the exogenous variables. By identifying these model components before fitting the model and comparing this list with the output from the software, this will provide additional checks to help us verify that the model has been specified correctly to the SEM software. And so here is a path diagram for this structural regression model. We have our 3 latent constructs or factors, F1, F2, and F3. We have our manifest variables, V1 through V9. We have error terms, the error terms for the manifest variables, E1 through E9, as well as D2 and D3, the error terms associated with the regression equations for the factors. The endogenous variables are variables that participate in the model as response variables in at least one equation in the model. The exogenous variables are variables that never participate in the model as response variables. And so we have F1, D2 and D3, and then E1 through E9. Moving on to step 6, we're going to fit the structural equation model in SAS PROC CALIS. Now, because covariance matrices are symmetric, only the lower triangular portion needs to be shown here and specified in the SAS data statement. And so let's do that. Let's create a SAS data set containing the covariance matrix of the 9 manifest variables. Here is the SAS code to do this. The data statement creates a SAS data set, which in this example, we're going to give the name cov. Now, in doing this, we've got to remember to specify type equal cov in parentheses after the name of the data set. Notice that in addition to the values in the covariance matrix, we've included a row giving the number of observed values for each variable represented in the data set. Next, let's specify the structural equation model in SAS PROC CALIS. Now, SAS PROC CALIS provides several different programming styles or programming languages for specifying structural equation models. In this lecture, we're going to be using the LinEQS modeling language. There are 3 main statements that we're going to use to specify the model in PROC CALIS. The LinEQS statement itself specifies the algebraic equations in the model. We use the variance statement to define notation and specify values for variances in the model. And then finally, the cov statement is used to define notation and specify values for covariances in the model. And so here is the SAS code to fit this model. The statement PROC CALIS invokes the CALIS procedure, and data equal cov tells the procedure which data set to use. The LinEQS statement is used to specify the regression-type relationships in the model. And notice that for the first indicator of each factor, we've set its loading equal to 1. And then finally, we have the variance statement. Notice that for each of the random variables listed here, we've defined notation that will be used to label their variance estimates in the output. So let's look at the results of this initial model fitting. So here we have a listing of the cov data set. And again, the cov data set serves as the raw data for the analysis. We don't have the original raw data on the 220 students that were collected, but we do have this sample covariance matrix along with the sample sizes, and that suffices as raw data for this analysis. Looking at the modeling information table, we see that we have 220 observations, and that matches what we should have. We are using the LinEQS programming style, and we are analyzing the covariance matrix. Next, looking at the variables table, we have a number of endogenous manifest variables and latent variables. So V1 through V9 are response variables, and so they are endogenous variables, and those are the manifest variables. We also have 2 latent response variables, or 2 latent endogenous variables, F2 and F3. We have 1 latent exogenous variable, and that is F1. And we have 11 exogenous error terms, E1 through E9, and D2 and D3. And so we have 11 endogenous variables and 12 exogenous variables. And so these model characteristics match up with what we came up with previously. Looking at the fit summary table, again we see that we have 220 observations specified to the model. We have 9 manifest variables. We have 45 moments. Now again, this is equal to the number of non-redundant entries in the covariance matrix, and it's equal to p times p plus 1 over 2. And so in this case, 9 times 10, which is 90, over 2, or 45. We also see that we have 21 parameters to be estimated in the model, and so that corresponds to what we determined before. And recall that the number of degrees of freedom associated with a model is going to be equal to the difference between the number of moments and the number of parameters. And so in this case, we've got 45 minus 21, or 24, model degrees of freedom. We also see this in the next table, and so this corresponds to what we calculated previously. And finally, note the large chi-square value of 52 approximately relative to the degrees of freedom, which is 24. And so the chi-square value is a little more than twice the number of model degrees of freedom. Note also the very small p-value, 0.0008. These indicate that the model fits poorly. And so let's summarize what we've done and what we've found out. The structural regression model has been specified to PROC CALIS using the LinEQS programming language. The model has been fit, the parameters have been estimated, and all indications are that the model has been specified correctly. However, several model fit indices indicate that the model provides a poor fit to the data. This would indicate that the model is too restrictive. It's not flexible enough to be able to fit the data well. And so this is not a good starting point for the model simplification procedures that we want to look at subsequently. And so the next step is to find a better fitting model. But that's going to have to wait until the next lecture video. I'll see you then.